Good. We can see it.
Okay. Is everyone ready?
Nice. Let's welcome our speaker, Russell Land, who is working with Dr. Steve Codden. Today, he will be talking about bias in association measure under mixture models.
Okay, thank you. Well, let me introduce myself. My name is Russell Land. I'm a graduate student at Georgia Southern, studying statistics. My advisor is Dr. Cardin, and this is a project we've been working on for about 2 semesters now. And then I want to thank everyone who organized the conference, Dr. Wanduku and everyone. Appreciate it. There were some good talks today. And then I guess just in the interest of time, I'm gonna go ahead and get into it. There's gonna be a lot of details I skip over, just because of time. But if you're interested in those details, my master's thesis will contain all that stuff, if you're interested. So, okay, I'm gonna be talking about bias of correlation under mixture models. Okay, so first I'm gonna do an introduction before I get into the main part. So consider measuring the correlation between 2 variables, but the sample is contaminated with observations from an unintended population. So we're going to answer the following questions. So as a proportion of contamination, P changes, how will this affect the bias? What form does the bias as a function of that mixing proportion take? And can we characterize the behavior of the bias in some way? And do different measures of correlation behave in different ways? Specifically, I'm going to be looking at Kendall's tau and Spearman's rho. So real quick, I'm going to do a quick example. So a statistician collects data where some data comes from valid and some is unwanted contaminated data. So these are just consider these 2 different distributions, both bivariate normal. These are just the parameters of both of them. Just notice one has a weak negative correlation and one has a strong negative correlation. So this is a kind of a visual of what the data would look like. So I'm gonna actually jump over to R and show you the rest of the example. Okay, so as you can see right here, this is that first distribution. It has a weak negative correlation, as you can see, and then just for visual aid, I just put the least squares regression line in here. So now I'm gonna mix in the contaminated data. So as I mix in just a little bit, over here, you can see the correlation has now jumped positive. The least squares line is now positive slope. And that's just a little bit of mixing. And then the more you mix, the greater that correlation gets until you get completely mixed data, which just means you sampled the wrong population pretty much. And you can see the correlation went back to negative. So just keep that example in mind as I keep going. You'll see it's just kind of foreshadowing of what's going to come. So here's the outline. So I just did the introduction. I'm going to introduce mixture models. And then I'm going to introduce the rank correlation. I'm going to define concordance and discordance. I'm going to go over the different rank correlation methods. And then I'm going to go into the main result, which is the bias of mixtures. And then we're going to do an example on the Marshall-Olkin distribution. Okay, so what are mixture models? So mixture models can arise from sampling unwanted populations. Consider a statistician collecting GPAs from undergrads on the Georgia Southern campus. So maybe the surveyor forgets to ask if they're a grad student or undergrad. You may get some grad students in that population unintentionally. So when this happens, it becomes a mixture of valid data and contaminated data. So I guess just for example, say graduate students have high GPAs. Well, this is going to affect any statistics you want to run on that sample. So more formally, this is how we define a mixture model. So let V, so the valid population and then the contaminated, be random vectors. And then let W be Bernoulli with parameter P. This is going to be our mixing proportion. And W be pairwise independent of the components V and C. So then this is how we define the mixture. So as you can see, each value will either be 0, 1, depending on P. So it'll either be valid or contaminated. Okay, so what are concordant and discordant pairs? So we're going to need this to define some stuff later. Well, a concordant pair occurs when there's 2 points that have the same sign when subtracted. In other words, it's when this x2 minus x1 and y2 minus y1, if they have the same sign, it's concordant. Visually, that just means they're increasing. And for discordant pairs, it's when the opposite is true. So if they have opposite signs, and then this would be graphically if they're decreasing. Okay, so let's go ahead and define the sample version of Kendall's tau. This is usually the most widely known definition of Kendall's tau. So given a sample of raw data, calculate the number of concordant pairs and number of discordant pairs, and it can be calculated by C minus D over C plus D. Also, n choose 2. So Kendall tau has a range from -1 to 1, where each extreme would be perfect correlation. And Kendall's tau can capture any type of monotone behavior in general. So here's some examples. So as you can see, it's strictly increasing. So Kendall's tau is 1. Strictly increasing, Kendall's tau is 1. And then here's an example of a negative correlation where it's kind of jumping up and down. Now I'm going to introduce the population definition of tau. So as motivation, let's consider this as the sample size increases. So I'm going to take the limit as the sample size increase goes to infinity. So I'm going to take the definition. We're going to split up the terms. Now, kind of think of this as probability of concordance, and you can think of this as probability of discordance. So, so just some motivation before we go into the population version. So let's go ahead and define that now. So bivariate distribution, consider a bivariate distribution with random pair xy. Let x1, y1, and x2, y2 be IID pairs. Then Kendall's tau of a population is defined with this quantity. Just a brief comment, this would be your probability of concordance and your probability of discordance. So yeah, if the two are subtracted and have the same sign, they'll be positive. If they're subtracted and have different signs, it'll be negative. Okay, now let's introduce Spearman's row. So the sample version of Spearman's row, you have x and y be real valued vectors, and let rx and ry be the ranks. So you take the ranks of those vectors. Spearman's row, the sample is the covariance of those ranks divided by the standard deviation of each. A lot of you may recognize this. It looks like Pearson's correlation coefficient. It is. It's just on the ranks of the data. So Spearman's row is similar to tau, where they can both capture general monotone behavior. Rho also has range -1 to 1. And then observe Spearman's row is Pearson's correlation on the ranks. And there's also cases where you consider ties. We're not going to consider that because we're going to be working with continuous data, which can't have ties. Okay, here's some examples of Spearman's row. So increasing, both 1, and then you have this negative correlation here. Now we're going to talk about the population definition. So the population definition and sample definition aren't easily connected. So we're going to skip that. In the meantime, let's introduce the population version. So this time we have a bivariate distribution with random pair xy. Now we have 3 IID pairs, all independent. So x1, y1, x2, y2, x3, y3. Then we define Spearman's row as this quantity here. So you'll notice it looks similar to tau. We have this constant scalar out here. And the other difference is instead of having independence between x1 and x2, we now have independence between x1, x2, and y3. So we have that extra component of independence there. Okay, and then I'm going to show you these equivalent forms. So let x and y be continuous random vectors with CDF fxy, with marginals fx, fy. Those same population definitions I just introduced can be written in this form as well. They're equivalent. So tau xy, you have this constant out here, double integral, and you have a CDF integrated with respect to the CDF, -1. Now we'll look at this later on. It's called a Riemann-Stieltje integral, and we'll look at how to integrate those. Spearman's rho, similar deal here. We got a scalar out front. Now we're doing the CDF with respect to both marginals, and then -3. Let me also mention there's also a third equivalent definition in terms of copulas. We've been working on that, but just in the interest of time, we decided to not include them. Okay, so now that we have that out of the way, let's go ahead into the main result of this presentation. So let V, so we're going to be talking about the bias under the mixtures. So using similar notation as before, let V, C, M for the mixture, W and P, the mixture proportion, be described as in the mixture model. Then the bias under the mixture for both tau and rho with respect to the mixture proportion is tau of the mixture minus tau of the valid. And same goes for rho. So we're looking at bias in terms of the mixture proportion. So as we mix it, how does the bias change? So now using this idea, we'll introduce the main result of this presentation. So how do we define those bias? So the following theorem will present the idea of the bias in terms of P, the mixing proportion. Note that if there's no mixing, then the bias is 0. So the bias in Kendall's tau and Spearman's rho due to mixing can be expressed as these equations right here. So we have a scalar out here. Notice that 4 kind of came from that integral definition. And then we have these coefficients here, and it's a quadratic. So the bias of tau is a quadratic with respect to P. Rho, similar form, it has the bias is a cubic function in terms of P. Now we're going to define the coefficients, which is the fun part here. So we've got the first coefficient for tau and the second coefficient. It's a little overwhelming at first. I just want to point out we have Riemann-Stieltje integrals, and each one of these integrals is an integral of a survival function with respect to another survival function. It's just different rearrangements of that same integral. But we can take advantage of that when we actually evaluate it. So instead of doing all 4 integrals, we only have to do 1 and then replace the parameters correctly. So same goes with rho. So here are the coefficients for rho. We have a integral of a survival with respect to two marginals. And it's the same kind of case here. We have 8 different integrals. Again, we can take advantage of that, of evaluating one integral and just changing the parameters at the end. And then here's the other coefficients. So these are just linear combinations of those same 8 integrals that we just saw. Okay, so obviously we're going to skip that proof. But it's actually not that bad. The important step involves taking advantage of the linearity of integral differentials. So here's the property right here. So if you have 3 functions, f, g, and h, be real valued functions, and let a, b, c be real valued scalars, then if you have an integral of a function with respect to other functions, you can distribute those and pull the constants out, which came in handy. Okay, so now let's look at the different root behaviors of quadratics without a constant term. So if you notice, this is the form that the bias of tau takes. Well, there's different cases we can consider. I'm not going to go through each case. I just want to point out there's different cases for the root behavior. Graphically, though, I think it'd be easier to show. So here are the different cases. We have the bias is always positive, negative, negative, and they all start at 0. And then if you guys remember from that first example I was showing you guys at the beginning, this is kind of an example of that, where we had the correlation increased and then decreased at the end. Well, in this case, we have the bias is increasing. It's positive and then goes to negative, and then this would be negative to positive. Same thing for rho. So we have root behavior associated with a cubic without a constant term. And again, I'm not going to go through all these cases, but there's a lot of cases for the cubic. And graphically, we can show all these. And there's 2 pages of these. So they look really similar to the tau case. We have these cubic behaviors down here as well. Okay, so now we're going to do an example using a bivariate distribution. So I'm going to introduce the Marshall-Olkin distribution. So this distribution arises from shock models and its ability to predict the failing of a 2-component system. So just think of a machine with 2 moving parts. We're going to let Z represent the occurrence of the shocks. So this would be the shock to the first one. This would be a shock to the second component, and then this would be a shock to both. Now the Marshall-Olkin is defined as the first variable is the minimum of the shock to the first one and the shock to both, and then Y is the minimum of the shock to the second and the shock to both. Okay, so as we saw in that theorem earlier, we need the survival function. So we're going to go ahead and find the survival function for the Marshall-Olkin. And here's how you find it. So you end up with an exponential function. With this max term here is going to introduce some problems, but it's something we can work around. Here's a visual of the Marshall-Olkin with just various parameters, all 3 of those lambdas. I just want to point out we have this cusp here in all of them. It's easier to see on this one, and that comes from that max term. And we'll show how to get around that problem when it comes to integrating this region. So we've got the survival functions and the CDFs. Okay, so using the definition for the bias that we defined earlier, we can find the bias for both rho and tau under this Marshall-Olkin distribution in terms of the mixing, how much contamination there is. So beginning with tau, like I was saying earlier, we can save a lot of time in calculations by noticing each integral follows a similar form. Therefore, we can solve one with placeholder parameters, and the actual integrals just need the parameters plugged in the correct spots. So I'm going to show that right now. So just consider the dummy parameters alpha and beta for now. And then here's Lee's theorem. This is a lemma we're going to invoke when we solve the integrals. And this lemma is going to help us get around that non-differentiability cusp that I showed you on those graphs. So if you have 2 CDFs and you have an integral of one with respect to the other, it's equal to this quantity here. Okay, so let's go ahead and solve that general integral for tau. Invoke the lemma, do some calculus, and then we end up with this expression here. Notice with alphas and betas. So say we have the Marshall-Olkin distribution of the valid population and then the contaminated population. Well, to solve all of those integrals, we just have to notice we have the valid here, contaminated here, and all the other different scenarios. We just have to plug the parameters in the correct alpha and beta positions. So here's just an example of evaluating one of those. Okay, so once we did that, I guess a natural question would be to ask, are all those cases possible? Well, we simulated this experiment and we found that yes, you can find parameters such that all those cases are satisfied. So let me show you those graphs again. These are actually those cases. And then we can do a similar process for rho. So what we're going to do is plug in dummy parameters, so alpha, beta, and gamma this time, because we have to account for the survival with respect to the 2 marginals. And we go ahead and solve. And we get this expression in terms of alpha, beta, and gamma. And then similar to tau, we'll consider the following integral. We just plug in the appropriate parameters. And this would be an example of solving one of those integrals. So we have the valid, contaminated, invalid. And I probably should have mentioned earlier, when you're doing these integrals, it's equivalent to doing the survival function or the CDF. They will both give you the same answer. The reason we did the survival function is because it's a more compact equation. So again, can we get all those cases with rho? We can. So we simulated an experiment and we found all these parameters that satisfy each of those cases. So again, here's all the different cases that the bias can follow. And just the unique part about the rho is it's a cubic function. So there could be situations where the bias actually increases, then it decreases, then increases again. Okay, so in conclusion, so what questions have we answered? So bias is introduced into models depending on the proportion of mixing. So whenever you have contaminated data that comes in, bias will be introduced. So we can characterize that bias for Kendall's tau under a mixture model as a quadratic with respect to P. And we can characterize Spearman's rho under a mixture model as a cubic with respect to the mixing proportion. And then we saw every case is feasibly possible. Some may be more common than others. So what questions have we not answered? So there is potential to represent these calculations in terms of copulas, a function that can capture the dependent structure between marginal distributions, which is something we were working on, and maybe something for future work if we can get it to work. And then there are other association measures that can be considered. So Cronbach's alpha, that was one that we were going to talk about today. Given enough time, we didn't have enough time, but it was analyzed in a previous paper by Dr. Carden, Trevor, who's was a grad student here. He's at Clemson now, and Nick Holtzman from the psychology department. So that's the end of the presentation. So I guess I'll open it up to questions.
Yes, Russell.
Yes.
I like this, what you're doing. I think it's a good thing. And actually I learned something. I didn't know how to associate with Kendall's tau and the other one. Can't remember what it was.
Spearman's rho.
With their population equivalent.
Oh, yeah.
It's, you know, with the population correlation, I understand how that's defined. So thanks. Second thing, though, I wanted to ask about, you said something about you can't have ties because of the X and Y data, the X and Y random variables are continuous. Well, theoretically, that's true. However, when you started simulating, then you have to at some point, you're going to stop at so many decimal places.
Right.
Since I think you're doing nonparametric, you're probably not going to have large sample sizes. But how many decimal places do you need before you can practically eliminate the possibility of getting ties?
That's a good question. I think for this project, we more focus on the theoretical side.
Mm-hmm.
We didn't encounter any ties when we did the simulation. But I guess that's something we could look into because there are, as far as I know, for the sample definitions, there's different definitions of Kendall's tau based on if there is ties, if there's not ties, and same with Spearman's. Well, actually, I don't know about Spearman's rho. I think Spearman's rho automatically accounts for ties.
Could you just throw out those cases that you end up with a tie, just eliminate because you're saying this is not really being generated by a continuous variable?
Actually, Russell, can I jump in?
Yeah, go ahead.
We did simulate some data early when we were more in the investigative stage, trying to figure out what was possible. And then we tried to get a point where we could do all the calculations analytically, which is why we ended up working with the Marshall-Olkin distribution. It was one of the nicest bivariate ones that we could. So actually in this, there's no simulation of data. In order to find out if all of those possible cases for the quadratic and cubic could actually occur, if they were feasible for Marshall-Olkin, we randomly generated parameters for each of those, but actually did not generate any data randomly.
Okay. That's an interesting way to do things. I even hadn't thought about that, so thanks.
Oh, yeah, I learned a lot doing this project.
Always do.
I'll say that
Actually,
paper
what
by
I,
Kruskal in 1958 is especially interesting.
actually, what I tend to learn is how ignorant I've been. As I learn more, it just seems like there's so much more I could have learned. You begin to think you're really ignorant after a while, but I say when you look forward, you should take a look. You say, look at all the interesting things I could work on. You have to look backwards to see where you come from to measure your success. My 2 cents. I'm gonna mute myself.
Do we have any other questions?
Any other questions?
I've got just a comment, maybe question, whatever you want to call it. These are, when you look at this, these are measures of association in, if you look at the contingency table setting, you have the difference between concordance and discordant pairs. You have so much D, you have Kendall's tau, Spearman's rule, and all this. So in essence, rather than look at this difference in concordance and then relate it to contaminated model in the discrete and the continuous setting, would you think that this can be applied or used when you have a discrete setting? Your model, there's a continuous model, the bivariate Marshall-Olkin. What happens if you have a discrete model?
Yeah, that's a good question.
I guess it's a mixed question and a comment.
Yeah, that's an interesting comment. Dr. Carden, did you have a response to that?
No, just we had enough trouble with the continuous one that we didn't move on to discrete yet. We have thought that if we do try to extend it, we found some interesting multivariate definitions of both rho and tau. And at least one of those was from a paper by Harry Joe, and I know that Professor Kim talked about him earlier in the day. So that may be the extension that we go with next. What happens if we look at higher dimensional forms of association?
Yes, I think that would be very useful, especially if you look at this general notion of dependence in multivariate random variables, in particular discrete random variables, because a lot of these measures has been characterized one way or the other to involve this notion of dependence in ordinal contingency tables, because this so-called Kendall's tau is actually a measure of dependence. You can look at it as a measure of dependence in ordinal contingency table. It's a discrete setting. So that's one thing that you can look at.
I think the discrete case is pretty interesting, but Professor Stephen mentioned, I think the multivariate case is now working. Harry Joe and JMA, they published the paper, and also new direction now from German, Claudia, many Claudia, but her name is Claudia something. They did fine copula. Fine copula means pair of copula extension. So if you use pair copula, fine copula, maybe there is good extension for your work. Then you can publish good journal too.
Yes, that's right. That's right. You can actually look at this in terms of copula, and then get a better idea of how these measures can relate to tail dependence or what have you, depending on what you're looking at.
One of the problems we ran into is we did try to do this with copulas first, and almost everything worked. But even the copula form for the Marshall-Olkin is closed form, and it's very nice to work with.